So currently we are in the top module, in which here are the inputs. The first one being the clock, which is a 100 megahertz clock to the FPGA signal. Reset is what resets the game. PS2D and PS2C are keyboard data and clock from PS2 signals. The H-sync and V-sync are VGA sync signals. The 12-bit color output is being stored in this RGB register. We have implemented the state machine declaration. The first one is the new game, which is the start screen state. The play is the game running state. The new ball is what the state which comes after losing a ball, and the over state is the game over state. Then we have a 2-bit register, and state next. The state register stores the current state, and the state next stores the next state. Now, then we have the signal declaration. WX and WI are the pixel coordinates of the VGA signal. W bit on is the visible screen area, WP tick is the pixel tick, graph on is the game objects active, and the hit is the pedal hit, and miss is when the ball is missed. The text on is when we decide which text is to be displayed, and the graph RGB is the color from the game, and the text RGB is the color from the text. Then we have the 12-bit RGB registers and RGB next, which stores the final pixel colors. Then we have dig 0 and dig 1, which scores the current score, and it is for storing the digits. That one dig 1 is for the test digit, dig 0 is for the ones digit. Now, GRS still is to pause animation, decrease is to increase score, declear is to reset the score, and to for timer start, the timer start is for the start delay. Now we have the timer tick and the timer up. Timer tick is a 60 Hz tick, and the timer up is when the delay is finished. Now we have 2-bit ball register and ball next, which tracks the number of balls, which is the lives we have. After that we have a 2-bit state register output and wire, which is the over output, the outputs from the other modules that has to be stored in these. Then we pass the current state externally, and over output equal to 1 if the game is over. Now this is the instantiation of the keyboard submodule, which is being called. It takes key A and key S to move the paddles. Now we have the VGA controller, which has the output pixel coordinates, XY, sync signals, and pixel timings. After that we have the text module, which has the score, game over, press start, and uses dig 0, dig 1 to score, and ball register for lives. After that we have the Pong graph logic, in which we handle the movement of the ball, the pedal movement, and the collision detection. Here the inputs are key A and key S, state registers, over, and output is the hit, miss, and graph RGB, which is for ball hit pedal or not, if it missed, or what is the color of the pixels. After that we have this assignment, which generates a tick once per frame for 60 Hz, used for timing units. After that we have called the timer module, which is pauses before new ball and pause before restart. After that we have the score counter, which has the score increment, score reset, and speed increase. Now we move on to the sequential logic, which runs for every clock edge, and if reset, then resets everything, starts new game, ball is 0 or color black. Then we have to change the state, so we update the state and the ball count. Now if WP tick is there, then we update pixel colors only on this condition being true. Now we move on to the next state logic. This is the implementation of the FSM. Now we assign the initial value or default values to grayscale as 1, timer start to 0, D increase to 0, and declear as 0. Now state next is the state register, and the ball next is the ball register. these are assigned. Now, if the state is new game, the ball next is three balls, that is 1 1, and declear is 1. So we clear and we reset the scores, and then we assign three values to the ball. And if key is pressed, any of A and S, then the state changes to play and the ball count is reduced by 1. Now, if it hits the pedal, we increase the score. Else, if it misses, then we decrease the ball count. After that, we have the new ball state in which we wait for the timer to be up or any key to be stored to move on to the next state. This is the final state, which is the game over state. Now, if the timer is up after the game is over, then we change the state to the next game. So we wait for 2 seconds before going from over state to the next state. We don't wait for any keyboard inputs. After that, we have the RGB output logic. Now this chooses what to display. If WVD on is not 1, then we make the screen off, which is black. Now we move on to priority rendering. Now if text on this logic is true, then we show text first, else we show the game objects. Other than that, if this is true, we show the game objects, and for this we use the aqua background. The final output is then stored and sent the color to VGA. Now we will look at the keyboard module, which was called in the top module first. So it takes the inputs as the clock, which is the system clock of 100 megahertz reset, which resets the signal PS2D and PS2C, which is the PS2 data line and PS2 clock line respectively. We have the key A and S, which is high when A is pressed and S is pressed, and key release when indicates that the key release event. Now we have some internal signals. We have 8-bit D out and a wire RX done tick. D out is the received data byte from the keyboard, and RX done tick is indicate the 1 byte received. Now we have a special Verilog keyword, supply 1, which is constant logic high. So the RX enable always stays high, meaning PS2 receiver is always enabled. Now we have an 8-bit key which stores the previous key value. Now PS2 receiver. This is the module which reads serial PS2 data and converts it into 8-bit scan codes. Now output D out, which scans like 1C, 1B or F0, RX done tick, which is the new data ready. Now key processing. Now we see if the RX done only executes when a full byte is received. Now if the key is 8 tick HF0, then F0 is a special PS2 code. It means the next key is being released. Now after that we set the flag key release as 1, else we keep it to 0. That means the key is still pressed and not released. After that we have the key A, which is equal to 1C and key is not released. So if 1C is there, then we assume that the key A is pressed, and 1B when S is pressed. So this was our keyboard module. Now we move on to the VGA controller module. Here also we have the inputs as the clock, which is the 100 megahertz clock for FGA clock, and reset, which resets everything. We have video on, which tells if pixel is visible, H sync and V sync for horizontal sync signal and vertical sync signal. Pre-tick, which is pixel clock, which for 25 megahertz, X and Y current pixel positions. Now we have the parameters. HD, which is the visible area for 640 pixels, HF, which is the front watch, back watch, and the sync pulse. These are the three. Now finally, the maximum resolution which we can get is the sum of all minus 1, which is 799. And similarly for vertical, we have got the VD, which is the visible rows, as 480 pixels, and for VF, VB and VR, similar to the horizontal, we have got vertical, and the sum of them minus 1 is 524. So our resolution comes out to be 799 to 524. Now we have the clock divider, in which the 2-bit register and the wire W 25 megahertz. Now we check this and run for every 100 megahertz clock signals, and it repeats a cycle from 00 to 01, 10 to 11, and then it repeats. Then we generate pulses high once every 4 cycles. So the 100 megahertz by 4 comes out to be 25 megahertz. Then we have the 10 bits register for H count, which is the column X, V count, which is the row Y. Then we have the sync registers, which store the sync signals. Now we do the main register update. For sequential logic here, if reset, then we reset everything to 0. Else we update counter and sync signals. Now for horizontal counter, we do the same, and similarly we update if the reset is not equal to 0. After that we have the sync signal generations, in which horizontal sync pulse active during retrace period and vertical sync pulse. Now we have the visible area only true inside when x is 0 to 639 and y is 0 to 479. Outside it is a blank screen. The final outputs are then assigned and sent sync signals to the monitor. X and Y are the pixel positions and P tick is the pixel clock output. Now we have the Pong text. So the Pong text also has the uh, clock input, which is the clock similar to all other modules. The ball is the number of lives, is it 0 and is it 1. It stores the scores of the game. XY is the current pixel position. Text on tells us which text region is active, and text RGB tells us the color of the text. Now we do the ASCII ROM connections. This is the font memory, which in which input the addresses, output 8-bit rows of pixels. So each character is 8 into 16 pixels block. Now this module divides the screen into 4 regions. The screen on, which is the screen plus ball, the logo, which is the Pong title, the rule on, which is the instructions, and the over on, which is the game over. Now for uh, every part of or region of the screen, we have done the character mapping, and we display score, balls, Pong for each region of the display. These are the rules. Use two balls buttons to move paddle up and down. These are all displayed after the character mapping is done. Now after that we do the ASCII rendering logic, which combines character row inside characters. Pick single pixel bit, and if bit equal to 1, draw pixels. If bit equal to 0, then we keep on the background. So if text RGB is assigned to 12 tick H888, which is the aqua background, which we assign the background color. Now if score on is the uh, region we need to display, we use the color red, and if rule on, we also use red. For logo on, we use blue, and for game over also we use red. Now the text signals. Now we assign the 4-bit signal, bit 3, bit 2, bit 1, bit 0, which is the score, logo, rules, and game over. So this is how we do the text for the game. Now we move on to the graph logic. Here also we have the clock reset, which is similar to others. Key A and key S are the paddle control. GRA still is freeze game, start game over. XY is pixel position. Video on is the inside screen. Speed up is increases difficulty. Over in is resets when game over. Graphs on, object exists at pixel. Hits ball or misses the ball. Graph RGB is the color. Now screen limits are set to 639 to 479 pixels. We have the refresh tick which generate 1 pulse per 60 Hz. Now we have the wall definition. The L wall L and the left wall right is given 32 to 39, which is 8 pixels. Similarly, for the top, bottom, all are given 8 pixels. Now for the pedal, we have given 4 pixels, and for the uh, pedal height we have given 72 pixels. So the pedal is 4 into 72 pixel, width is 4 pixel, and the height is 72 pixels. After that, we move on to the pedal setup on the right side, which is given to 600 and 603. So it is to the extreme right of the screen. Now we have the ball setup. So now ball size is given to 16, and then this ball register is the ball position, and this gives the initial speed to the ball. Now if we see, we want the ball to look something like this. For that we have used a sequential logic, and we have assigned the ball this shape, which is looking similar to a circle, not which makes it close to the circle but not too far away from the square. So we are avoiding the square ball over here. Now this detects the ball, and if it hits the ball, it is bounced back and the direction is changed. If it is moving down and hits the ball, it is made to move up. So this was the graph logic. This controls the ball movement, detects the collision, increases the score, and decrease the ball count based on the results. Now we have the timer module. In this, we also have the clock reset. The timer start and the timer tick are the one which starts or restart the timer, and time based signal. And timer tick is the time based signal of 60 Hz from VGA. Timer up is the output which becomes high when timer finishes. We have some internal registers, which is the timer registers, and the timer next, which is a 7-bit counter, which has the maximum value of 127. Then we have a sequential logic in which runs for every clock, and if reset is there, then the timer register is assigned to 127. Else the timer registers is given the timer next value. The next state logic is assigned by the combinational logic, that is, if the timer start is there, then the timer next is given the value reset timer to 127, and then the countdown, that if the timer take and the timer register is not equal to 0, then timer take is equal to 1 and timer not 0. Now the case 3, hold the value. Now if timer next is equal to timer register, there should be no change. The final output is assigned to the timer up, and the timer register is equal to 0. So this was the flow for the timer module. Now we have the counter, which keeps the track of the scores. This module implements a decimal counter for the scores, and it generates the speed up signal as the score increases. Here also we have the clock and the reset. Decrease is the increment of the score. Declear is the clear score. Digit 0 is the ones digit, and digit 1 is the test digit, which stores the score. After that we have internal registers, which is R digit 1 and R digit 0, which stores the current score digit, and R digit 0 once and R digit 1 twice. Now the 5-bit total score is what stores the full score from 0 to 31 range approx. Now we come to the sequential logic. Now if reset, then R digit 1 is 0 and R digit 0 is also 0. So we start from the 0 0. Now else, if we update to the next values. Now the combinational logic, this one. Now if it is done, the digit 0 is assigned to the registered value. Now it holds the current value. and then it clears the score, then resets it to 0. Else if the increment is there, then we check if there is an overflow in the ones digit, then we increment the tens and then set the ones digit to 0 once again. Now if digit 1 is 9, digit 1 is and digit 1 next is 0, then the maximum is 99. This is reached. Now we need to update it to 0 0, so we will use reset. After that, the total score is assigned by add digit 1, which is the tens digit value, which is multiplied by 10, and plus the ones digit value. So this gives us the final score. Now we assign digit 0 to the R digit 1, which was used for temporary updation and all in the logic, and digit 1 is assigned to R digit 1, and this would be passed to the top module. So this was the complete flow of my project. Hope you guys loved it. Thank you for watching.